Thank you. So, good afternoon, everyone. So I will just give some quick review everything that we did tomorrow quickly. So it came to my knowledge that the link for the codes was not working if you don't have a Google Drive account. So I've redone everything. And now if you don't have a Google Drive account, you can already download. This you just need to click on the link. And if this presentation with the new link is already on the timetables of the conference. So if you want, you can just go to the website. So yesterday we discussed about how we solve the ODEs. In the case of the PDEs, they are more complicated, and you will need some professional solver, something that my colleague Jorge Delgado will talk on the Thursday and Friday. So stay tuned to that. We use a fourth and fifth order Runge-Kutta method with an adaptative step, which is written in a C language, and the second algorithm that implements boundary conditions. We here use this implement this program in the Boson Star case. In this case, the spherically symmetric Boson Star. So we saw that we have some kind of we have three kinds of equations that can be written in the following form, where we put all the lower order derivatives on just one side. We can also obtain the origin approximation and the asymptotic approximation. For the case of the Boson Star, this symptotic decay, since we want asymptotically flatness, imposes a symmetry scale invariance that will ultimately just change or rescale the value of omega and the sigma. Sorry, can you just please close the door? Please? Thank you. So, in the case of the adaptative step, so today I have a better website with a better internet connection, so I can show you here some GIFs. So in this case, we have the case of the Runge-Kutta method, which is the usual integrator, which uses an intermediate step between the step that we know and the step that we want to know. In this case, for the animation, we only have a second order because it's to be simple. And this intermediate step does not have any physical meaning. It's just to compute the proper correction for the last step, the one that we want to obtain. So we obtain this. In our case, we will use for the adaptative step the dormant prince, where we have a table with all those coefficients that enter in the intermediate steps. And in the end, we compare two different order methods, but with the same table for the intermediate steps, which will allow us to only compute these intermediate steps once. So we saw the integrator scheme. We saw that if the step size after we compute the error is large enough, we have to change the time step and we do all the computation. Else, we already have the solution. For the case of the second strategy, this method is a shooting method, which is created to compute the roots of functions, which in the end is more or less what we want, because we want a root at infinity. We want that the system will decay asymptotically flat. And we can use this kind of strategy to implement boundary conditions. This is the second method because you do constant seconds to the curve that you want to obtain the root. Okay? So we saw all of this. We saw that we have a symmetry property for the sigma 0. How we do the shooting, we have to redo everything if you don't have the error, enough error. Oh, sorry, if you don't have accuracy enough, or if we are not close enough to what we want. Else, we advance to the next solution. So we have three files. Today, the file Boson Stars will not create a single solution, but will create the entire domain of existence, or at least from the starting point. So, but before that, let us study a little bit the data. So this is more or less the profile of a single solution, the solution that we obtained yesterday, where we can see that the blue line is the sigma and tends to 1 as it goes to infinity. In this case, our infinity is very small, it's 20. But you can see that at around 10, all the functions are all more or less stabilized. And this approximation is good enough. For the mass, it also stabilizes to the ADM mass, and the scalar field decreases to 0. So as we expect, this decay is exponential. For the domain of existence that we are going to obtain today, we obtain an in spiral. These are all rescaled proper values, and we observe an inward spiral. This inward spiral is common for the majority of these bosonic objects, like Boson Stars and Boson Stars with self-interaction. As we go inside the spiral, we have an increase in the density, but it also has a change, since you see that the mass also changes. And we are going to be able to obtain all of this, okay? So, but before, you can see, just one quick point, you see that, imagine like 0.85, there are more than one solution that contains the same frequency, but different masses. So, and this corresponds to different solutions. You can see that as we go inside the spiral, which will correspond to the second omega with the same frequency, we have a higher initial scalar field amplitude, which is very important for what we are going to do next. Because as we go inside the spiral, since it is very easy to see, since it is for omega equals to 1, which is the starting point, we don't have any mass for the Boson Star, which corresponds to a trivial solution. We expect that as we go inside the spiral, the initial scalar field will increase. So that's what happens. As we go inside the spiral, the amplitude of the scalar field at the origin increases, and the Boson stars become more compact. This is very important because this is a property that can distinguish between two solutions with the same frequency, since the mass we only obtain after integrating. Okay? With this solution and with this code, we can also obtain excited states. So this is, I think it is the 9th excited state. After you obtain one of these solutions, it's very easy to follow the solution and obtain the domain of existence. Okay. Any question about this? No? So let us now study a little bit how you obtain and extract the data. So for the solution, I have here, and I've sent you the mathematical code. I will not run it because it will crash my computer, but it's in your computer. Probably it will work very fine, very well. My computer has 10 years, so it doesn't. It's not. Sorry. This is the solution point NB. Okay. Yeah. Yeah. So I've prepared all the codes. All the codes you can see here when you extract the files. I prepare all the codes to run as they are. Okay, you can just run. You don't have to change anything. You don't have to change any directory. Okay, so that's something that I will explain now how we do it. So first, in the Mathematica, it's very important for you to set your directory. In this case, since I'm using all the files in the current directory in such a way that you can just run the integrator and then compile the Mathematica without changing any in the folder, it's the name. But if you don't want, you can just put here with the two primes, maybe, the directory of your file. Then one very important and very useful property is this set option, which saves automatically the notebook. Every time you run a cell, it saves automatically, which can save you a lot of work. This is a game changer. Very useful. Yeah, these two lines. One says where it goes to save, and the other does the autosave. This thing is when you have a computer that's constantly crashing. Ooh, I mean, this is very good. And then you have just the usual cleaning. Okay, if your computer is weak, you can just separate the cells, and they will work separately. Okay. Here you do the import of the data, which is the solution point data, which has the solution that we obtained yesterday, which contains the profile of all the properties. X is the radius, P is the scalar field, S is the sigma function, M is the mass function, that is the derivative of the scalar field, and there is the error of our adaptative step. You can change the name. The name doesn't matter. Okay. Then we have just a file for the solution parameters to avoid you to have to input it. This is just some properties of the solution. And then here we put all the functions in a table form in such a way that we can integrate after. Yeah. Here we just print the global data. It's just to see if everything is working well and if you are not observing anything wrong. As imagine that since you know that at the origin you are expecting an absence of mass, this number must be very small as it is the final scalar field. So these are something that you can check here. It's just some preliminary tests. Then I here compute the profile. This command on Mathematica is very heavy. So I'm just warning you because Mathematica to do plots, it's not that good. If you want to do quick plots, try to use GNU-plot or something like that. But it's useful because it's here and it's safe. And here you can see the plot of the error, the step size error. This is, as you can see, they are very small, around 10 to the minus 21. Okay? It can be even smaller, but then it's a matter of the accuracy that you implement in your code. Okay? Due to the properties of Mathematica, we are also able to do some interpolation, which allows us to do numerical integrating. In this case, I numerical integrate the Noether charge with a better integrator than the Euler method, but still you can see that the difference is not very small. This is the Noether test. You can see that it's very close. So that short computation can give very good accuracy for our study. Sorry. Then here we compute this is just a computation for the scale test to see if our integrating point is far enough. Usually I put this around 5 times the radius of the Boson star. You have to take into account that in this case of these bosonic objects, they do not have a hard surface, so you cannot define properly a radius for these objects. So one of the ways that we can do this is to compute the point at which 99% of the scalar field is inside. Okay, that's what we do here. We compute the 99% of the scalar field and observe that it is around 99% of the mass. Exactly, that's what we computed here. The radius. This is just the yeah, that's correct. Sorry. That's what we computed here, the radius. Here is just a scale. Okay. Yeah. Then you compute the compactness. These are just some properties that we can quickly obtain. But most important of all is the numerical test. Sorry. So for the numerical test, we use the Komar mass test and compare with the ADM mass. And observe that it is very small, even for this kind of numerical integrating, which is in part due to our numerical or adaptative step. So, and the virial identity, we also compute it, which is probably the strongest result that we have, and gives 10 to the minus 9. Okay. In fact, you can do the same as we did in the video with the Noether charge and put this computation inside the integrator. But as you can see, these codes are not that easy to do, to write on the code. And depending on what kind of C program you are using, Mathematica has a function that is called C-form. I think George will talk about this, about the Fortran form. But for this, the version of the C that I use, this C form does not give a good results. So it's better just to write it by hand and then do the debugging, which can be quite a pain. And then would like to write this, all of this. Okay. So this is just one solution, but we want the domain of existence, the complete domain of existence. Is there any question about this? No? So, to obtain the complete domain of existence, we cannot just obtain one solution. We have to obtain several solutions. Okay? And that's what we do in this code that is in the folder domain. So, let us go below. The folder domain that has the codes. Integrator domain.
Alexandre?
Yes.
When you have a question in the room, can you try to repeat the question loudly?
Oh, there, Antonio was asking where are we going to do? Where are we going to open the file now?
Okay.
Okay. Is any other question? So, is it okay?
Yes.
Okay.
Just say the codes, just say the names.
Oh yeah, because this. Yeah. So if you go to the domain folder that I sent the link before, there is the face.c file. One of the good things to, as I talked yesterday, of having separate functions which are very general, is that I just had to copy this function.h and this integrated.h, copy into this folder, and call it in face.c, and it will run. Since it's compiling, since it's working very well, you just have to call this and compiling this face the main file, and everything will work. You don't have to redo everything again. That's something very important that you should do. Okay, so as you can see in this block, it's exactly the same as we did before in the to obtain the single solution, but now we want all the solutions until omega equals to 1, because that's, well, you can put 0, but it will crash on 1. That's something that we'll know a priori because these kind of solutions are already set. If you don't know this, it will become a research work, and you cannot do this kind of stuff. You can have to search it by yourself. You have to put it like 0 and see where it crashes, why it crashes. In this case, in that case, will be a research problem by itself. Okay. So one of the parameters that we can change, we can do a shoot. Since we are doing a shooting for phi 0, one of the parameters that we can change and is not, and this characteristic of the solution, of each solution, besides the phi 0, is this omega frequency that is not yet renormalized. So this is one of the things that we can change, and that's what we do. Every time we run this code, this cycle, every time we obtain a solution, we go to this, we actualize our frequency and decrease a little bit. And after decreasing a little bit, we redo all the thing with a new guess. But this new guess, since we know that the more or less the behavior of the initial scalar field amplitude, we know that it decreases as you go outside the spiral and increases as you go inside. We can, it has a monotonic behavior. We can just change in the end, after doing the shooting, we can just change the initial scalar field amplitude, which will give a better guess for the next computation. Okay, I don't know if I was clear enough, but what we are doing is giving for the next solution the better guess from the previous one that we obtained previously. Okay, so this is a cycle. Okay. Then you have to do again the renormalization, and you print here all of this stuff. Okay, this is again for the plot. This found.2 is just a file that extracts all the generic quantities if you want to import in Mathematica. And this print, it prints on the terminal. I use, if you want, you can just comment this, and it will run faster. So every time you have to print something, the code, it's like an if cycle, it will have to stop and print in your terminal. So if you want, you can just comment this and it will become faster, but you will not know how the things are working. And if you have a code that takes 1-2 days, and in the end of that time you will see that it's not working correctly, it's better to take a longer and be sure that it's working well. Okay, and this fprint, it does the same but for a file in such a way that if you want, you can have all the initial conditions for every solution. Okay, so if you want to obtain one solution in the other code, you go to this file, which is called a structure, copy and paste the values that are there in the initial condition of there. I mean here. Okay, if you want, we can then obtain one isolated solution here. But it's just to change the omega, the final radius, and the final scala in the initial scala field. Yeah, about this final radius, we also have to do some updates, because as I told you yesterday, this this final radius will change as we change the compactness of the Boson star. And since we don't want to observe that exponential divergence at the end, I mean, because where is the, if you don't mind, can you see? So if you do the profile of the scalar field, it will decrease very close to 0, and then at some point, some numerical problems, errors, it will diverge very fast. Okay, and you want to avoid that. So you want to put your integrating before. And one of the strategies that, in my case, I use is just to see if the total mass, or at least 99% of the mass, is in the first half, or more or less in the first half of the integrating points. In fact, this is much closer to the origin than half, because you will have much more points at the beginning than at the end. So this will probably be like 1/5 or something like that. And then if this condition is good, you can just decrease the step, else the step is increased. Okay, and then you have to redo everything again. And then this is just a plot. So, okay, the plot and the time. Okay, I will put this running. I will not finish because this part is the one that takes longer. And but that you will see how the kind of result that it extracts. Let me just take this out, or my Mathematica notebook will not run in this case. So you just open the terminal again, and put the command for it. Okay, then you'll see something like this. Okay, you'll see that your frequency is decreasing. This frequency that has not yet been renormalized, as it is the initial scalar field. Okay, and the radius is changing depending on how compact your object is. What I usually do, because this will be a rogue estimate, is then when I want to study just one solution, extract this data, increase the radius until the point that I can, increase the accuracy, and just run one solution. And with that, you can have very high accuracy results. Okay, so now just I'm almost finishing. Study the mathematics, to study the domain of existence. Again, we have the header. She's common. I just copy and paste. You don't have to change much. Then I import this domain of existence. Here I'll do some data treatment, which just to put this in a table form to plot, and you obtain something like this just from one run. You obtain the mass and the Noether charge. I mean, I said that you take a lot of time to run this, but in my desktop it took like 4 minutes, something like that, which is not much. And then you can also extract the global data, the point where the maximum mass, the minimum frequency, the maximum Noether charge, and the total number of points. Okay, and with this, I finish my talk. Now I would like, if some of you have problems, if some of you are trying to run and have some bugs or some questions, if you want, you can share your screen, and I can help you to run this.
I have just one for fun, but I got 2 dots instead of this.
Oh, where?
When I in this plot in this, I run the Mathematica.
Oh,
face.md.
yeah, because this is the face point ND. Yeah, 2 points because you run the code this face point C. If you run it, have you run it?
I run something.
So because since I put this to work directly, if you run this, you have to run until the end, because Mathematica will extract that file.
Okay.
That's why I took these 2 dots point slash from this file. Okay. The data that you already have, I've already compiled it, but you can run it since you have an airplane there. It will compute very fast. Okay. Yeah, that's because of that. You just compute 2 points, or just save 2 points. More questions?
Sorry.
Yeah. So for the ones who are out there in the world, there was a question here: how we compute the divergence. So why we have this divergence? Okay, so let me. I'm sorry for the ones that are there, but I have to give you some. So your scalar field decays as exponential of minus square root of u square minus omega square, something like this. Let me write it this way. Okay.
Alexandre, can I ask you something?
Yes.
Can you write either approaching your camera, just making the zoom, or writing in a bigger letters? I mean, now it's okay. Now it's okay.
Let me see. Okay, it's okay. I will write in here. Okay. Okay. So you have like u square minus omega square times the radius r. Okay. So this will decay very fast, but it will also it decays extremely fast. If you don't take care about this, you don't know your Noether charge, because you don't know it, because this will have some amplitude here, and in fact will decay as r, but this is another term on the decay. So this decay will decay like 10 to the minus 20 very fast, because it's very small, or it can be very high, and the radius will decay very fast. So numerically, you cannot control this. Okay, your numbers, in this case, we have double type of your for your variables, which is just 10 to the minus 6. If you want one double, you have 10 to the minus 16, I think, something like this, or 20. But it's still far. Okay, so there will be errors just from this round. Okay, and this round, since this is exponential, it is very fragile. It will diverge very fast. Okay, if you have a massless term, master scalar field. Your term will be something like this, just the scalar charge over R. Okay, and then you can integrate up to 10 to the 6, whatever. Okay. Just because of this exponential term. You cannot, it became so fast that you cannot combine. You cannot keep it up with it. That's the only reason. Okay. Okay. More questions? Can you see that? So, is there any other question?
I just would like to ask, a lot of the variables that are declared in the files are long doubles. Is that kind of accuracy absolutely necessary?
No, but I mean, it's better to have long double than just double because mainly because of this divergency. You see,
I see, yeah.
every time you have, I told you this yesterday. Every time you have some numerical integrator, you have addition of errors because this is a discrete method. So if you can avoid this kind of round errors, just to the lack of accuracy, it's better. And since we are using so few variables, this does not take so much space. I think it's better. It's just a good habit for you to have.
Okay, yeah, yeah. But it's just not every language supports long double types.
What do you mean like that? No, sorry, can you repeat?
Yeah. So, for example, I was yesterday. I was like translating the code to Julia just to try it out.
Yeah, yeah.
And Julia doesn't have support for the long doubles natively.
Oh, okay. Yeah, but if you want very high accuracy and for a large enough radius, this long double will you will notice the presence. So in fact, this code already have some time and it has evolved. In the beginning, it had double, just double, and you saw the difference I saw the difference when I changed from double to long double on this the stability, manual the stability of the code. Because these solutions, sometimes you have square roots, exponentials, and just very small points can give you huge differences.
Yeah, I get it. Thanks.
Yeah. So,
okay, so if there are no more questions, we can I think we can wait until we start next.
yes.
Make a break, a coffee break. So next session is starting at 3. So 3 p.m. here.
I don't know if Fabrizio Di Giovanni has a question because he wrote thumbs up. Do you have a question? Fabrizio? Oh, I don't know if
He could be writing.
Oh yeah, he's writing. Okay, yeah. So
Take
you
your
can
time and write it down.
Yeah.
Take your time.
Can you hear me now?
Yes.
Yes?
Yes.
Oh, okay, sorry, my microphone was not working. So yeah, I have a question. How do you evaluate solutions with excited state solutions? You just put some conditions to have a profile with some nodes, or there's something else?
So imagine that. Let us imagine that you don't know the solution. You don't know these initial parameters. Right? It's
Yes.
exactly the same problem. If you don't know the solutions for the excited states or for the fundamental states, then what you have to do, which will be the worst part of all of this, is just input some parameter and go changing the initial scalar field. Okay, you will see that the excited states will appear first, then the fundamental state, and since you have a shooting, you will obtain always asymptotically flat or a solution that tends to 0 at infinity. So you will obtain several solutions. You have to do this. This is the worst part. You have to do it by hand.
Okay.
After
sorry. Just continue, please.
So you start like 0.1 and go increase it by hand until you observe the fundamental state or the excited state that you want. After that, you just decrease the guess range and put here the initial scalar field, and your solution will follow that solution. Since you have a guess range so small, let me show you this guess range. Since this guess range is so short, so small, the only possible solution that you have for this scalar field amplitude is the one that you are following, the excited state or the fundamental state. These are strategies, okay? Probably there is other strategies. There are other ways to do it.
Okay, so you mean that you keep all the parameters the same and you change the value for the initial value of the scalar field until you see some solution that have some nodes, something like that?
Yeah, until the solution that you want. Imagine that you want to obtain the third excited state. You keep all these parameters and change the initial scalar field until you decrease, because this is the fundamental state. You decrease until you observe that solution. And since we are doing the shooting, it will tend to some solution. Okay, if you change this, it will tend to some solution. It can be not the one that you want. So that's a problem. But that's the worst part. You have to do it by hand. And honestly, I don't know how to do it other way, or never had the necessity to do it in another way. Okay. And then you just follow the solution. You just have a train line and you follow the train line.
Okay, thank you.
Okay.
Okay, so I suggest that we make a 15 minutes break, maybe a little less, and we reconvene here at 3 o'clock. So 3 o'clock Western European time.
Okay, sounds good, Antonio.
Okay, good. So see you in 15 minutes approximately.
Recording.